All right, so this talk is not about really programming languages or different kind of technical stack and so forth. Really about concept and idea. The same thing that you see in this presentation can be applied to different programming languages, from Erlang to Python. I'm going to use .NET here. How many .NET developer in the room here? Pretty much, I was expecting 3/4 in the room. Pretty cool. But again, you can take the same concept and apply it to your programming languages here. So why we're here? Well, computer can calculate complex numerical computation in a blink of an eye, right? And in theory, they are more powerful than human brain, right? However, human brain still outperform computer in several tasks, such as decisional tasks, right? I can give you two images, and you can figure out the image with a cat and image with a dog much easier than a computer. So artificial intelligence really try to overcome this limitation and use tool to make computer able to make decision based on knowledge. And one of these tools is neural network. I'm going to cover neural network here, but mostly in a different flavor. So who was here in the previous talk? We talked about like more high level. However, here we're going to talk more like a deep technical and figure out actually I can build your own neural network. So what's really the value of this talk, right? Why you're here? Well, because this is not just a neural network, but how you implement neural network with a different programming model, the actor model. And we'll talk about all this term coming shortly, but I want to just give you like in advance the main values, right? So one of the main challenges when you create a neural network is define the topology, right? How many layers, how many neurons, what kind of activation function, and I'm going to cover these terms later. And there is not really any set of predefined rules you can use to build the perfect neural network. It's about try and retry, change your model, and so forth. It takes time because the problem that I was facing is that every time you make a change to a model, you have to go through to change your code, select the training algorithm, can be backpropagation, particle swarm, and so forth. Then you train your model, test your model, verify the accuracy, and then you stop. If you're not satisfied, you have to repeat again this loop, right? Modify the model, and so forth. But the problem is always to stop. How about some sort of approach that you can change the behavior of neural network at runtime without ever stop? You can change the topology, add the layer, remove neurons, change the activation function. Without stop, never your system, right? And this actually is a great advantage because now you can really build a neural network that self-train. This is like everybody says, neural network can self-train. Well, no, really, because every time you change something, you have to retrain the model most likely. But this way, you can probably push your code, your neural network in production and make it run during the day. And during the night, maybe you can switch in training mode with zero downtime. And the neural network can train itself again with the gap with just the data that you receive during that day. In addition, the other benefit is that neural network, to me, is not complex, but still requires some attention, especially in a traditional manner when you have a lot of matrix operation. You have a lot of for loop, nested for loop, and it's always easy to miss an index, and it's very hard to figure out the problem in your code. Instead, with the actor model, we'll see it's all about passing messages, and we remove completely the idea of matrix operation. It's going to be just about addition and multiplication. If you know addition and multiplication, we can build easily a neural network using the actor model. It's not just about performance, although it's a positive side effect. But the real benefit for this approach is that flexibility and simplicity, okay? We can build a neural network here very fast, quickly, because you can run a script that can go through a different kind of option, adding layer, removing neuron, and so forth. And then in the end, when you run a different kind of different topology, you can pick the one that had the best output. Does it sound cool? Very cool. All right. So about you, familiar with machine learning? Okay. Specific neural network? Okay. This side here seems to be more okay. Functional programming. Very cool. I like that. This will be more. And actor model, most likely. There was a presentation Sean created this morning, very cool, as actually a nice follow-up. I won't use Net that was presented this morning. I'll use something different, but again, you can use, Net, proto-actor, any sort of kind of actor technology. So the main motivation is that I introduced a machine learning a little while ago, and I, for work, and I built first for an e-commerce a recommendation engine, and that was my first, experience in machine learning. And then I moved forward with a bit of natural language processing, and we introduced in that specific case actually neural network, and I got very fascinated how this kind of artificial neural network construct really can work, but it feels like it'll be too magic, like a black box, right? There are a lot of libraries out there, great libraries like Keras, TensorFlow is a big hit these days, but you end up when you use this library that you just clean your data, right? You pick up your data, clean up, make it more, massage it, make it pretty, so actually this library is able to understand it better. So you just feed a library and you just get the output. Well, I'm a geek, right? I want to know actually how this is work. So I like to open this black box and see this how it works, actually become a better programmer in this way. So that's why I started actually to build around my own neural network. In this presentation, we'll see two main neural networks. There are many different neural networks, right? But the feed forward, which is probably the easiest one, when all the neurons are connected, all the neuron one layer are connected to the neuron or the next layer. And it is very much commonly used for prediction kind of neural network. And the self-organized maps, this is a little more interesting because the difference between these two, the reason because I pick, is that the first one is supervised and the second one is unsupervised. And the second one actually kind of self-learn as it goes, which is quite cool. By the way, if you have any question, shoot me, interrupt me right away, better answer when you're in context. And all the material, sample and slide are on GitHub. I'll give you the link at the end so you can download it and play with that. So what kind of problem neural network solve, right? Well, if any of your problem can be answered by this question, most likely, you can use neural network. I've probably for the back of the room, you can read. This is the unsupervised kind of problem you can solve. This is supervised. There's the classification. For instance, when you have tried to group some sort of information, maybe to figure out if your email is spam or not, right? Prediction, of course, is when you have a series of input, maybe like a time base, you can use maybe to predict the future stock market, right? The value of the future stock market, and so forth. Optimization, the one we're going to see for what is the best route with the self-organized map, which is a classic problem. There is the travel salesman issue, and so forth. And neural network is actually is used in many different kind of branch and fields, right? We have healthcare, biology, robotics. These days, a lot of talk about self-driving cars, which have to adapt in the environment, receive a lot of information in real time, and make decisions that can make the difference between life and death in real time, right? So it have to be fast. So how are you going to achieve this kind of precision, right? Well, you have to create a very solid, robust model. So what is neural network, right? Well, artificial neural network, I should say, is the attempt to replicate the biological brain and really how a brain works. I like this quote because it really said that it's a complex system, but it's able to be adaptive, self-adapt, right? Through the flowing information that it receives. So the idea is that when you build neural network and you create this model, it's interesting when the neural network actually is able to get better over time, right? And keep self-training itself. Think about, I'm from Italy, and I like soccer. Anybody like soccer here, right? Well, when you start to play soccer, you go to the field, you get the ball, you start to look around how the player they're playing, kick the ball, figure out, how this is work. And it's not easy in the beginning. It's very satisfying when you kick the ball the first time, but it takes some time to become actually an overpaid player, right? So you keep training yourself over time, kick the ball better, keep the corner, until you reach your goal, right? It was okay. Anyways, so this is actually the classic example where you can use neural net to predict some sort of information, right? This is to predict kind of sport a student play based upon some pre-knowledge information. We have the student, we know the grade, the GPA, the age. Well, we have to predict what kind of sport plays, right? So we have used his input here, and this actually will be used to train our model, right? Now, I actually point out this slide. This is kind of easy. We're going to go something more complex and sexy later. But something that actually nobody actually mentioned when you talk about a network is something called normalization. And actually the first issue that I ran when I started to use neural network. And so what does it mean, normalization? Well, you have to convert and sort of transform the input you're passing to the neural network in some sort of meaningful values, right? For example, GPA is a number. It's pretty easy. Probably you can scale down, make it easy. Age, the same. But gender, what do you think would be the classic value for a gender? What? Well, it would be usually, it can be. So one mistake that is happening actually to me is that maybe you use like 0 and 1, right? That's not correct, because 0 is minimal. It doesn't have any mean, right? So the right value could be +1 and -1. So what I say that normalization is something you have to face. It really changes depending on your domain and so forth, but something to keep in mind. All right, so how this is neural network work, right? And this is probably the last boring slide, but from the biological brain, we know that neural network is this interconnected system of neurons, right? And where they transmit this signal, this electrical pattern. So the dendrites receive the input, and then the dendrites send the message to the neuron, and the neuron, when it receives some sort of chemical weight, it fires up. It makes some computation, some calculation, and push the resulting output, an electrical signal, to the axon terminal, to the next neuron, until you reach your output. Okay, that's a lot of buzzword, but let's talk about more technical, right? So this is actually how we try to replicate the biological brain, right? This is the classic definition of artificial neural network. We have a divide by layer, and each layer have a certain number of neurons. So in this case, this is again a feed-forward neural network, because each neuron are connected to all the neurons to the next layer. Okay, with this arrow, which is a connection which carry a weight. So this actually is a neural net of 3, 4, and 2 neurons, but usually you count only 2 layers. So this actually is a 4 and 2 neural network. The input layer usually is not counted. So this is the more important slide of all this presentation, right? How this really works. So the blue circle here are the input neurons. So just dummy, doesn't do anything. That's why you don't count it. So each neuron here connect to the neuron of the next layer, the green circle, with this arrow that carry a weight. So I'll be in more detail. All the input here carry a value, which is the input 1, 2, and 3, and send a connection to the next neuron, which is the input and a weight. So where does weight actually come from? Well, there are 2 ways that this weight come from. So in this case, the weight 0, 0 is index is 0, 1, we have 0, 5, and 0, 9. So when you start and you have you have to train your model, right? Which means that you start with some sort of value that over time going to be updated and change during the training process, and until you reach the final model, which is going to be able to give you the most close possible output to the expected result. So really at the beginning, this value is just random. You just load up the model with a random function, and maybe you can tweak it to make it better close to your domain, maybe from -10 to +10, I don't know. But really it's just random values. Now we're going to see later, during the training model, this value is going to be updated with some simple calculation, right? Going to be a comparison between the output and the expected result, some error calculation, and then sent back to update this weight, this random value, to make it be closer and better, and rerun it, and repeat this process for many, many times until you get the closest possible value. Then you're going to save this value. You're going to save this model. So next time you don't have to train anymore the model, right? So now you actually have a well-defined set of weight. So you're going to create a neural network, your model, you just send this weight, and you're good to go. So in this case, it's really turned out to be a very simple math, right? In this case, this green circle, the neuron, when it receives all the input, all the connections from the previous layer, it receives the necessary weight to fire. And what does it mean, fire? Well, it will just do a dot product with the sum of the product between each connection, the input and the weight, plus the result of the product between the second connection and the weight, and so forth, okay? When these all calculated, it's going to pass the result to an activation function. We're going to see later what is an activation function, pretty simple. And that's it, you have a result, right? There is also a bias there, but bear with me 1 second. We're going to talk about bias in 2 slides. But this is it. Then when you go to the second phase, and all the neurons of the second layer receive this value and fire up, you repeat the same process for the next layer, okay? You get all the input. In this case, the neuron is the input of the neuron, the last layer, the output, receive all the connection from the previous layer, which is, again, the weight and the value of the neuron. When all the value are received, you're going to apply the product, the dot product, apply activation function, and you get the result. That's it. That's pretty much it. Any question about this part? There is more into it, about training and a few other things, but higher level, this is actually neural network works. Okay, so in more details, this is the perceptron or neuron, and we see that we saw in the previous slide we have this input value in the weight that are passed to this neuron, right? Which then outputs some sort of value that they pass to the next layer until the final result. There are 2 things we didn't talk about it, the calculate error and the update weight. But this part just the training and how you update the weight during the process, which we're going to see shortly. But this thing about bias, right? So what is the bias? Well, it's just a value that is used to shift your basic output some sort of direction, right? If you're familiar with the Cartesian plan here with the axis x and y, pretty much you know that your function fx equal something usually you have plus bias, right? Which pretty much where you have the line doesn't start completely from 0, 0, right? It can be like +2, -1, and so forth. So pretty much this is just the bias. It's an arbitrary number that helps you to shift the value in the direction that you're looking for. And also this value is random in the beginning. Also this value is going to be updated during the training process until you receive your model. So activation function, this is like, take it really as it is, right? There are this activation function that the main goal is to squeeze and massage the output in some sort of meaningful range, right? For example, if you have a decision between 2 values, right? If you have decide if a student going to pass the test, yes or no, well, the sigmoid function is most likely the function to use because the output can be 0 or 1. The tangent usually I never see it for output, usually for hidden layer, the one that stay in between or your model, and the range is like -1 to +1. What does it mean? Is that usually when you have this dot product of your neuron, you have some sort of value. Can be, I don't know, let's say 0.46, right? Well, when you pass to the tangent, well, actually 4.6. When you pass to the tangent, most likely this value is going to be reduced to some value between -1 and 1, sort of, scaling. And the softmax, the last one, is the most used when you have some sort of prediction, right? When you have, especially when you have to decide between more than 3 values, right? 3 to 10 value. And then give you the output, where the output, the sum of the value of the output is always going to be 1. And most likely going to pick the higher value, the lower value, depending what you're doing, right? But really the main idea is scale the output to an appropriate range. And this is really, this is predefined, you don't have to invent it, right? Just to Wikipedia, figure out how this works, and just convert in your code, and that's it. So this is a traditional way that you see implemented. This is like C#, but it can be Java, C, and any sort of C language, right? But you can see how it starts to be complex to put in paper what we just saw in the previous slide, right? We have this for loop that get the input, and then the hidden layer do some sort of matrix operation, and then nested loop because to get for each layer all the neuron and so forth. Now, back to the initial reason, the value of this talk is that every time you change something here, is some code changes, right? And they require some testing. And it's, again, I had to get a paper, a pencil to figure out if I'm good with the index or not, right? So it's kind of painful. It would be nice, actually, this is completely abstract. It just reduced to simple multiplication addition. You can change this value, this topology at runtime without change your code, right? So we talk about training, and training is the process that we need to use to figure out the weight to use and that produce the best result, right? The most commonly used is back propagation. Is probably, I don't know if the oldest, but one of the oldest for sure. Is very easy to implement, and it's called back propagation because you have to wait that all neural network is completed to get the output to use to calculate the error, the gap, and then called gradient. It's just a fancy name to for the error between the output and the desired output, and then go backward to update all the weight, all the neural network, and then you run the second iteration, and so forth. There are other training algorithms. One is has some trend these days, is the particle swarm. Say that they get a better result. However, the trade-off is a bit lower than the back propagation one. I personally get better result to back propagation, but you can use either one. And as I said, it's pretty easy to implement actually. So training, the last part here is how you decide what to train. Well, usually you have a predefined set of values, right? Let's say you have 1,000 values. Most likely you're going to train your model, take between 70%, 80%. You're going to train your model, go to the training, use the back propagation, update the weight, and then when you're done, you're going to test this your model against the remaining 20% of your values, right? Now this is called epic. Most likely you run more than one epic. It can be like 100, 1,000 epic. And every time you run an epic, these 1,000 of value, they're going to shovel together, mix up. So the next epic, the 80% is going to be completely different from the previous 80%, okay? And you keep running, and that's called epic. So the reason because you run that many epic is because you want to have a very accurate neural network, right? And this is done calculating the mean error, right? Which is the average of all the error of the training data. Now, to train a neural network, we need to minimize this error and lower as possible, right? And the most common way to calculate the minimum error here is using linear, oh my God, I forgot the name. Dashed gradient or linear gradient? But anyways. Was it?
Gradient descent.
Yes.
Gradient descent.
Yes, that one. But so this is like the ideal world, right? Unfortunately, to calculate the minima, in reality, we're something a bit more complex, right? So there was some study, actually, it turned out that it's pretty easy to figure out how we reach still this point. And it's something called momentum. And momentum is just a value that you add to when you calculate when you train your model. There's just a value that is able to push this value up this peak, this slope, right, to reach your minimum. So this is, again, a little bit of code to show how you can build, in a very complex way, the calculate error. However, we're going to see how this can be simplified. Here, the momentum is just this constant value that I was mentioning. They're just going to be added to your calculation to be able to move forward. All right, so any questions so far? What's up? Okay, losing your noise, Friday, and we're, it is 4 o'clock, so it's okay? Keep going? All right. So let's build a neural network, right? So I'm going to use functional programming here in a few slides to give a high-level idea how you can just simplify what we just saw. And the reason because I use functional programming is that you can really think about neural network as a function. You have input and output, right? And you want to reach the point where whenever you pass the same input to this model, you can always get the same output, right? So in this case, whenever you pass the same input vector, you're going to get the same output vector. In functional programming, why it's fit quite well in neural network is because the composition aspect, right? Let's say that the output this function match the input on the following function, you can match together, you compose together, right? And so you have a function that's going to be represent your layer. And whenever the layer, you're going to pass the output to the next layer, you can compose the layers. You compose this function, right? Of course, neural network is a bit more complex. It's not that linear, but the concept can still be applied, okay? So how this is possible? So let's say I have these three functions. The append function, and you can see quite easily, it takes a value, a vector, and I'm going to append the value of the vector. Pretty easy. So now with that, we can apply the function and just use a specialized function to append the bias. And the last function, the layer, we just put everything together, right? You can see we have the activation function, which is a function that takes a number float and output float, pretty much that's what it does. A series of weight, which is a matrix in this way, and the input, which is my vector, which is just like a matrix with one column, right? And you can see here we just have the product, the weight, we sum the product, the weight, with the vector map, and the plus is just a function. Pipe the result to a derivation function, and append the bias. Pretty much, we have a layer function that when I pass the input, we're going to get the output of the neural network. Okay, so in this case, I defined a sigma function. No big deal. We have a few matrix here operation, which is our weight. Sorry, a few matrix, not our weight. And here you can see because I can use my function layer, passing my sigmoid, passing the matrix 1, and I use this operator that in F# used to compose the function, right? So now we create this function here, compose to the second function, which is the second layer, until to the next function, right? And pretty much it. Now we have created this simple neural network. Of course, this is a simplified, just work with 3 layers, but you can use an aggregator function like a fold. You still have this compose function to have any number of layer, and we just execute, which is compose, network compose all the function together and run it. Pretty simple. But let's go actually to the main part of the talk, right? We have neural network is a group of nodes connected, right? What does it mean? Well, that sounds familiar. When you think about networks that are connected to each other, I done some work in the past using the actor model, and to me, really, I started to think about they really map quite well with the model, right? We have the, in this case, an agent, but what it does is a unit computation that reacts based on a message, okay? You send a message to the agent, and receive the message, there is a behavior, which is your logic, right? Receive a message, can be an integer, the behavior just an addition, it does an addition, no big deal. And there is a state, okay? So actually, the agent can contain a state. It can be, the number that can be added and so forth. What is interesting here that is completely asynchronous. The message can be processed once at a time, and the other incoming message is a buffer and wait to be processed, okay? So really the interesting part here is that the agent really do one thing in isolation and communicate to the other agent, in this case the neurons, through message passing. They're completely independent. And I thought that I was discovering the coolest thing ever. But I wasn't the first one. So I found actually this paper, very cool. I forgot to put the link, but I'll put the slides later. This paper online that I read was very fascinating about they distribute the work actually across the cluster computer, right? Now, performance-wise, you have to really have a huge neural network to overcome the extra overhead introduced here. But the idea is very cool, especially for the benefit you get that all you can change topology at runtime. So in my opinion, one, you can use this approach to create your model. They take time, but this way you have a shortcut, it's more flexible, simple to use. And then when you have your model, the weight, the bias, the function, you can use any sort of programming languages, any sort of technology you want to use. You can use create this using C#, Net, and then use Python. I don't know. Because I want to adjust number, right? And second, if I ever want to build Skynet, this is the way, right? So again, this is the same idea when you have a small neural network distributing among computers here, and each are connected to each other through message passing, which is very cool. The benefit here is that the actor or the agent can have to capture the behavior of the neurons, because there is slightly different behavior between the neurons that belong to a specific layer. I'm not going to go in detail that, but for instance, when the output, the last layer, is a softmax, well, it's a little bit different from an output that doesn't use softmax, right? Because the calculation is slightly different. But overall, in this way, using the actor model, you can change behavior in the actor based upon the message you receive. So I think it's very cool that you don't have to change anything. And again, so it supports several types of neurons, and it's able to interact. Now, if you think about it, this is like the classic topological neural network with, how many layers? 2 layers. Good, good. And this is the slide with the most animation ever done. Think about this with an agent. It really mapped quite well, right? Pretty cool, right? It doesn't change anything, the structure here, because the agents are connected to the messages, using messages passing to all the agents of the next layer, right? And you remember that you have each neuron's way to receive the value, the input from the previous neuron, right? In this way, the neurons, the agent, is a way to receive all the messages to the neurons or the agent in the previous layer, and when they receive all these messages, fire up the operation, and then send the output to all the neuron or the next layer. So again, this is like the comparison between neuron and agent, but we have the connection, the neurons, the message passing, the process electrical signal where the agent reacts to inputs, to messages, right? So I really think that this way to implement neural net really click to me how this is work. Now this is a part of the code, but the main idea here is that this is an agent. I alias the name to neurons, but this should be mailbox processor, but it's easy to understand the neuron. And the start, just start the neuron, okay? Now the 2 arrow point 2 point. One, when the neurons start, the inbox receive the neurons wait asynchronously without blocking to the next message, right? Now, the flow here is pretty simple. Whenever I see the message, continue, append the connection to the current state, which is passed here in this loop, and then I check if the connection match all the messages supposed to receive before fire, if fire. Otherwise, is wait for the next message to be received until receive the complete number of inputs, okay? When I receive all the input, that's it. I sum the bias with the product of all the input and pass the output to the derivation function, and then I just pass the result in parallel to all the neurons on the next layer. I don't have any matrix multiplication nested for loop. It's pretty cool, right? It's 2 lines of code, and then I just broadcast the result to the other neuron. Question on this part? I'm not losing you, right? Yes?
You mentioned the advantages here? Like,
Yeah, in the beginning.
Elegant, but like,
Yeah, in the beginning, I mentioned that this is actually allowed you to change the topology of a neural network at runtime, right? Because one of the problems that I had is that, okay, I start with my model with 2 layers and, I don't know, 6 neurons, 8 layers, and second layer with 8 neurons. If I want to change topology, add a layer, remove a neurons, or even change the activation function 1 layer, I have to stop, change the code, rerun it. You can do all this stuff at runtime, and actually the beauty that you can create a script here, they can go through a different kind of topology, go through, and in the end, just have a fancy Excel chart and figure out which model had the best output, and you're done, right? Which is pretty cool. And in this way, actually, it's even easier really to have a neural network is able to self-train, because now, when I'm going to show you in the code, now there is one state which is called loop. Actually, in the code in GitHub is active and training, right? You have 2 states, and you can switch the behavior of the neuron at runtime. So actually say, I'm going to train you, and then I'm going to test you, and I'm going to in production. And then save the data, and then I have to train my model only with the data that I received since my last run that I trained, right? Does that answer your question?
yes, thank you.
Okay, so let's run a demo, right? Okay, so I'm going to show you first what's happened here, and then I'm going to show you a bit the code. So in this case, I define, what kind of the neuron for each layer. The input neuron going to be 4, then 6, then 12, and 3. However, the first neural network topology, you can see here, I add only 2 layers. 3 layers. Actually, not the input, 2 layers. When I pass, the value of the input here, my activation function, I have some learning rate, the momentum, as I mentioned earlier, just to train a bit easier in a ideal world. And I collect my data here. And this is the classic iris problem, where you have like a series of values that have been used to classify what type of iris flower, because apparently there are different kinds of iris flower. And based on the input, the computer is able to verify and which flower belong to. So first we train the neural network, then I stop in the console, just for intensity. I retrieve the model here. I persist it locally. Actually, I printed the model here. Persist it locally, serialize it to the local file, which is the model.dat, just for demo. Then I reload it, rerun it. Then I switch. Now I send a message to my network and say a switch. What does it mean? I pass from the training state to the active state. Okay? Then I pass just some value, some input here, and it's able to tell me the output correct based upon the training that just ran. But then I'm not happy. So I switch again. I add another layer here. I send this message. And again, this is going to be all runtime. I just put the console read line just to stop and go ahead
Okay.
by just add a layer. In this case, now we have a topology with another layer. Retrain the system, rerun it, and see if it's more accurate or not. Again, this is pretty cool because it's going to be all run at runtime, right? I run it. I did all the training here. That was pretty quick. I have all epic here, and calculate the error, and then calculate the accuracy between the expected value and the output here. Okay? I have accuracy, well, that's 100%, never happened before. That's good. I press enter here, give me the topology here, 4, 6, and 3. I switch. Now the neural network is not in training mode anymore, but in active mode. Press enter again, I send the input, and give me the result. Now the result is already based on the training that I ran. But now I say, okay, I press enter. Now when I switch, passing training, update my model with I add a layer here, and this is all random values, right? I don't care because now I'm gonna rerun again and go to the training again, and now it's worse, which is great because now we just have a proof that the adding a layer for this kind of problem, it doesn't have a positive effect, okay? Switch again, inactive, and run. It's pretty cool, isn't it? Okay, I know that this is a lot of console hub, and that's why I did in a color one. It's better. However, I don't know how to change the UI, so this is pretty much do the same thing here. Each circle is an arrow for each layer. You change the weight here, and just training all my model here all the way through. There is some UI involved, a bit slower, okay. But in the end, is able to calculate the accuracy and give me also a nice graph here with the value. Whoa, that's pretty nice, right? Or not? Okay, cool. So I have still 20 minutes, right? Okay. So I'm going to show you briefly the code here because I would like you to go on GitHub, download it, play, and send me an email if you have any question. But the idea is that you really define your model with different kind of options. So in this case, we have particle swarm, genetic, different kind of training model. But the main idea here, and you have to go through much of the stuff, I want to just go to the neuron part. There you go. This is actually the very cool part of this code, how you define a neuron. The neuron here, as I said, is as an alias to be a MapReduce processor. And this is actually two main functions here. Let's collapse here. We have the active function, which is the active state, and the training here. And this is pretty much all that you have to do. Now, whenever you receive a message here, which is from the layer, you can switch behavior and do something else, right? So in this case, let's say you start with the training here. In line 135, you wait to receive a message. Let's say you have switch, right? We saw the code earlier. What it does, well, instead to be a training here, you're going to pass the current bias and weight they calculate during the training and start from the active function. Sorry, the active behavior. And that's it. You can switch between the two different kind of behavior, and then you can do all the nice fancy stuff, adding, removing, file adjust value to trigger the operation and so forth. Very important, load and retrieve model. So every time you have defined a model, you can just save it, persist it, and run it later without do further training. Okay, so let's go back here. I'm going to gloss over this part here. I want to go to the next problem that I think is very, very interesting. So why parallel neural network? Like, because as we discussed here, neural network is this massive, can be a massive interconnected series of neurons, right? In this case, we have 500 connections. But if you add another neuron, you're going to add 19 other connections in this case, right? So really can increase the number of connections. It can be a quite large number of connections. So in a traditional way, we have this bunch of nested for each loop to compute, your training. That's why it's most of the time from the traditional way that you have, the for loop, you're going to probably use the parallel loop, or Keras or TensorFlow also can leverage the GPU to, speed up the processing. But the problem here during the training, that's what it takes actually time. And that's why I think the actor model take advantages of the fact that you can send messages and change behavior without turning down the system. So this is the way that you can calculate the learning rate in C#. So there are two main values here that can affect your processing. The number of epoch, of course. The larger it is, the better the system, but the longer it takes. However, you cannot be too large. Otherwise, let's say you have 1,000 input, right? Well, if you run, I don't know, many epoch, most likely you run a point that you have accuracy 100%, but you can have overfloating, right? So which means that it's very specific tailor for your data, and then we push in production with different data, you have a disaster. You don't want to do that. And the other value is the learning rate. And the learning rate is the value by which the calculation shifts the direction and the value of your learning rate. It can be like positive something, negative something. But the learning rate is really the value that is used to update the weight. Now, the higher it is, the faster is the training, but most likely you don't have a very accurate model. However, the lower it is, well, it's going to take more time to train, but also in this case, it can be very difficult, if you remember when I showed you to calculate the minima, to find the momentos to go across the peak, right? So again, how are you going to find the right number of epoch and learning rate? Well, you can't, right? It's just about trying different kind of values until you find the perfect one to the perfect match your desired output. That's why the actor model is perfect, because now you can change this value without changing your code. This slide here, if you buy my book, you will see that this is pretty much match the design of MapReduce, right? Whenever each layer do some sort of computation and pass the result to the next layer and so forth. We don't have filter, MapReduce, but most likely it's very similar, right? Still map here. And that's why we have this computation here that can be parallelized quite easily. But what I show you here from the functional perspective, MapReduce really comes, from the name of functional MapReduce. There's a bit much into it, you can filter, group by, but the idea is that you have two functions, high level. The map, of course, the reduce, right? And the functional approach here is that you compose the two functions together. If you remember, as I showed you earlier, with this funny fix operator, which is a double arrow, right? So now you have two functions here, and to create MapReduce, compose the map and reduce function. That's pretty much very similar to what we saw earlier when we create the function to define our, neural network. Very cool. So let's go to the last problem here. I'm gonna spend a little bit here, but I want to open for question. So the traveling cells problem, right? This is the classic problem about unsupervised training. And actually I discovered this is probably not just used for fun or for interview kind of purpose, but also used for the study of the DNA of the genome. And it's based on a map of two-dimensional, when each node represents a city, right? So in this case, the neuron is going to have two weights, which are the x and y, the location, the point of your plan. Now, this is a problem that is very hard to solve because I don't know if you can see it in the back. Okay, that's supposed to put some sort of animation here. But let's say you have like two cities. Well, the solution is pretty easy, right? If you have 5 cities, well, it's going to be probably under 20 because factorial. But you have like 500 city or 1,000 city, well, the problem is going to take a lot of time to be solved, especially with some sort of brute force, right? So that's actually where neural network can fit quite well. So I'm going to show you two approaches here. All right, let's do animation. Let's show two approaches here. One using neural network, and this is unsupervised. And the other one, actually, you can parallelize neural network. I found this paper here. I'll put this link here, which is quite cool actually how they did it, because now they solve this problem using classifying the city in a section, okay? Solve the problem in parallel for each section, and use a function called blend function that blend all the solution together, which is very cool. All right, so let's run the demo here. Oop. Close here, close here, close here. And the source code is here, so you can play with that. Just gonna run it. Okay. All right. Bugging. Should start briefly, I hope. It's thinking. It's so nice when the Visual Studio thinks so hard. Oh, there you go. Terminated. Yes. All right. Second time is a charm. All right. Oh no, that's actually the other one. All right. So. Okay, now it works. Who knows, right? Magic. So let's start actually with even more than let's 100 city, okay, 1,000 city. Well, probably too much. Let's die 500. Okay, well, that's too much. I don't want to be too crowded. But you can play with 10,000 city if you have a big screen. Okay, so initialize here. Let's start with the classic elastic neural network, right? You can see it spread around a lot of lines, try to figure out, and it took 3 seconds, 240 milliseconds. It's pretty fast, actually. So that's a run of 25,000 iteration. Of course, I update UI every, I think, 500. So now I can use the different approach here that I was telling you earlier, that use actually classify the city using k-means, but I don't want to go in detail there, in section here. And I'm going to run it here. Again, I'm going to explain one big difference here. All right, this it took 3 seconds, 326 milliseconds. All right, very similar. The result is still quite good. However, check the difference here. If I put 0 iteration with the traditional way, you're going to blow there a bunch of lines because I tried to touch the city because it's not supervised, right? Try to self-train something. And of course, you go ahead, second iteration, so for second iteration, it starts to get better and better, reduce the line to figure out the city. The other approach, although, is quite cool. It started a circle. It started a circle, it tried to touch a city, and when it touched a city, the second iteration started to shape as almost like an egg, right? It started to shape like an egg one side, and the other side tried to be touch the city to the opposite direction, right? Pretty cool, right? So completely different approach. Now you can leverage this approach, parallelize it, right? Let's put 2500 here, cluster here, let's run it. 863 milliseconds. Now that's good, right? And the idea, if you remember, actually, let's do one iteration here. No, the other one, sorry. Okay. It started as a circle, right? Now, I put as a cluster 4, but of course, you can parallelize by 6. Why not, right? And trigger this section is a cluster in this city, and then try to connect each section. But now this section will run in parallel, figure out the best pattern, and then blend it together, right? Which is quite cool. Let's put actually 3,000 iteration to make it better. Run it. We have 6. That's pretty cool, right? Thank you. Thank you. So, and it actually was for 3,001 iteration. I don't know why. But anyways, but yeah. So the code exactly use the same approach with the agent, right? We have or actor that communicate between layer using message passing, which I really recommend download the code and play with that. Now, saying that, I have 5 minutes left. So the goals here, the goals here are to simplify the approach to build your neural network. Because let's face it, if you use third-party library, it's great, but I think you want to know how this is work underneath it, right? And that's the garbage collector in managed languages, right? You really not to know how does it work. It works, it's fine. But if you know how it works, you optimize the code and make it run better, right? Same approach here. So neural networks solve complex problem, but it can be simplified the implementation just with simple linear algebra, right? And I think that it can be easy to be parallelized, especially the last example, when you can tailor your problem. And I think the actor model really represents a breakthrough. I didn't invent it, but I really think it's a great approach to build accurate model here. So that's all I got. I open for question, and this is all my information. Actually, something that is very cool. These two links, the first one is a workshop. So I recommend before download all the code and and see how this works, go to the workshop and try to play with that, right? Actually, it's kind of more interesting when you try to iterate and figure out how this is work. This is my Twitter handle, my information. Tweet me. And question. A lot of information for a Friday afternoon. And man between you and the happy hours, right? Oh, no, it's a keynote. Yes?
How does this compare to something more like TensorFlow, where it's like a different computational model?
Yeah, so TensorFlow, I use it. It's a great tool, but really like a black box, right? You don't know how this is work. However, you go back still to the benefit of this approach, that TensorFlow, you create your model, you run it, and you don't have, like, if you don't have an accurate result, you have to change your model, rerun it, change stuff, and so forth. This approach, I think you can do all this kind of changes much easier and faster. However, to be honest, whenever you get a very sophisticated model in this approach, you can then pass it to a TensorFlow and run in production, right? But I don't want that you get this code run in production, then you call me 2 in the night, say, Ricky, what do you do here? This is not working. But this is a great tool to build model quickly and accurate.
Does it distribute across?
So this is not the demo that I did, but you can swap use Ricardo.net to your cross machine easily. Yes, yes. Actually, the paper. So you can swap the implementation of the agent here with something that work cross-process across machine like Ricardo.net. So the answer is yes. And the paper, I'm gonna put the link and upload the slide. Yeah, you can do quite easily. So, any other question? All right, thank you for coming.